Okay, so we are starting off today with your all's favorite theorem. Today in our flip books, we wrote the 3 big theorems of calculus, and this is one of them. So the intermediate value theorem is also called the IVT, and in fact, the AP graders accept that as an abbreviation. So you can say by the IVT and then follow it up with whatever the intermediate value theorem told you. This is something that we saw in pre-calc, so it's not new to us, but it's just something that we need to see over and over to make it be as simple as it really is. So the intermediate value theorem, well, actually, somebody want to tell us what the intermediate value theorem is in your own words? Anyone?
Is it like if there's 2 points, then like all numbers can be in these 2 points or something?
Yeah, that's pretty much it. So I'm not sure how much sound this is going to pick up, if it's just going to pick up me or you all as well. We'll test it later. But it's telling us that we have a continuous function. That part is really important, so go ahead and underline it. It's got to be continuous. Otherwise, it does not. We can't apply the intermediate value theorem. We're not even going to try. We're just going to say it's not continuous, can't apply it. But if it is a continuous function, and sometimes we know that because of the type of function, sometimes we know that because the problem will tell us it's continuous. But if that's true, then exactly what Zeddy said, over my interval a to b, then that means I have every single y existing between f of a and f of b. Or the way that they say that, there exists at least one number x in a to b such that f of x equals k. So they're saying that you could plug in any number in between those x's and you're going to get every single number eventually in between f of a and f of b. What this is helpful for is determining if we have an x-intercept. That's helpful sometimes. We've looked at problems before where we've got our f of a ends up being above the x-axis and our f of b ends up being below the x-axis. So we can say if this is a continuous function, then by the intermediate value theorem, there has to be an x-intercept somewhere in there. Okay. So a lot of times we're being asked about a 0, but not always. The second example here asks us about a value of 1. So looking at the first example, we're showing that the following function has a 0 on the indicated interval. So they're not asking us, they're promising that there is a 0, and we're just showing it. So we're looking at, these would be our a and b. We're going to look at our f of 0 and f of 1. And what will have to be true if there's an x-intercept? Yes, sir. Yeah, we've got to have one of each by the intermediate value theorem. Now, if they're both above, that doesn't necessarily mean that there's not an x-intercept. It just means we can't prove it using the intermediate value theorem. We would have to go a little bit more in depth. So let's see, plug in 0, negative 1. That. 2. And there are so many things on the AP test that you may get a question and you're not exactly sure what it's asking, where if we had a free response question that said something about does this function have a 0 over this interval, and we know that we're using the intermediate value theorem, we're going to go ahead and give a good explanation of why we know this. So we've already, they didn't ask us yes or no, so we don't really need a yes or no, but we can say since, and we are looking for there to be a value below and a value above, so we're going to go ahead and say since f of 0 is less than 0, and f of 1 is greater than 0. And what else had to be true? Yep. How do we know? Say it again.
I was going to say just put the number of cosines.
Yes, what kind is it? Yeah, it's polynomial. Yeah. We have all of our x's are raised to whole numbers. We've got a polynomial, so it has to be continuous. So it could be worded probably better, but since f of 0 is less than 1 and f of 1 is greater than 0 and f of x is continuous, then there is a 0 where okay, so you could say in between, you could use more words there, in between 0 and 1, or you could just say over 0 to 1 by the IVT. There are definitely wordier ways that we could say that correctly, and there are less wordy ways that we could say that correctly. Some people might include f of x as a polynomial so they know that it's continuous. That's not necessary to get the points. We just need to state that it's continuous. But sometimes just following your full train of thought is best for you. You could also say since f of 0 is negative and f of 1 is positive, so you could be a little bit wordier there instead of using symbols. But we do need to say like one's below and one's above the x-axis. So I know by the IVT, and this is important, saying that that's the reason we know it. The intermediate value theorem is important. Okay, so let's go ahead in your groups look at example 2. So you're showing that function f of x takes on a value of 1. So this one's not talking about 0, but it takes on a value of 1 for some x over negative 2 to 4. So first, do we think that we can guarantee it?
Yes.
Yes, and again, this one didn't really ask us. It is telling you that we're showing that it takes on the value, so it should work. Something else that came up there, and Logan, I just feel like it's a good question, because intermediate value theorem is different in this aspect, that we really don't care what's actually happening. We also don't really care to plug in other values to try to investigate further. We only care about the endpoints, because the intermediate value theorem only states that if we have this interval from A to B, we're guaranteed the y values from f of A to f of B. That's all it says. So whenever we're investigating this, I'm finding f of -2, I'm finding f of 4, and those are the only values that I care about. If it ends up that neither of them, that they don't tell me that it goes through 1, then we would just say we can't say that it goes through 1, possibly, but by the intermediate value theorem we wouldn't be able to say it. Now we end up with -2 being -2, and f of 4 is 52. So does it have to go through a value of 1? Yeah. So for different reasons than example 1, we're not talking about being below the x-axis and above it, although they are true for that. One of them is below 1 and one of them is above 1, so it has to go through 1. Okay. So in our explanation, we've got should be saying that it is continuous. How do we know? Because it's what? It's a polynomial. I'm sorry, I thought you said it's positive. It is positive, but it's not very, I think I just misheard. So we've got f of x is continuous. For your explanation of being below 1 and above 1, you could literally say that f of -2 is below 1 and f of 4 is above 1, or you could use the same notation we used on the last one. Say f of -2 is less than 1 and f of 4 is greater than 1. So what are we trying to say? We'll remember our symbol for therefore. I'm going to throw that in there. You can use your therefore symbol if you want. Therefore, what do we know? Okay, so we know that for some value, for some x, and we could even use the words that they used here. We could say f of x takes on the value if we wanted to. Value of 1 for some x. So if you're ever not sure how to word things, sometimes the way that they asked it can help you a little bit. That whole last part, I just regurgitated what they said. Therefore, f of x takes on the value of 1 for some x in the interval -2 to 4. Okay, so my explanation is missing one thing. What is it missing? IVT. So you might throw it in at the very beginning. You could even just say, by the IVT, I do declare. So we could say it at the end, or we could say it here on our therefore. So therefore by the IVT, blah, or at the end we could say therefore we're guaranteed this by the IVT. But somewhere in there we do want to include our intermediate value theorem. This is what brought us here today. Okay. Questions on either of those? Okay. We've got some loose ends with our limits. So we've got some limits at infinity. I keep saying that we're going to re-go over Bobo Botten, and here we go. So our limits at infinity, the first thing that we are going to check is to check to see, check horizontal asymptotes. To see if the function is bounded. Because if we're going off to infinity, so all of these are talking about x going off to a positive infinity or a negative infinity. As we get closer to an infinity either direction, either it's going to be bounded by a horizontal asymptote, and so it's going to get really close to a certain value, either from the bottom or from the top. or it's going to go off forever. So we're going to check first to see if it is bounded, because if it is, then that will be what it limits to. Eventually the y values will get close to the horizontal asymptote. So for those of us that need this reminder, here you go. So you've got BOBO stands for bigger on bottom. Kind of weird for an acrostic, but you get a y equals 0. Your bottom is bigger on top. You end up with none. So in this case, we wrote this in our flip book earlier. If it is this case where there is no horizontal asymptote, that means that it has to go off to a negative infinity or a positive infinity. Is unbounded. Even if it has a slant asymptote, it is still going to be unbounded as far as continuing off to a positive infinity or a negative infinity. And then you could have an eats DC. So this one says exponents are the same. And we'll divide coefficients. So anytime we're using Boba-Botten, it's talking about comparing the highest power in the numerator to the highest power in the denominator. So that's what we're talking about here with the bigger on bottom or bigger on top. Exponents are the same. So what do we think for number 1? Will it be bounded or not? It will. It will be bounded. And what is it going to bound to? 0. Okay, so we're just saying we're bigger on bottom. The highest exponent is on bottom and x to the first. And so I've got a horizontal asymptote at 0, and so wherever my function's at, above or below, eventually, as I go further out to infinity, it eventually will get closer and closer to 0. All right, how about number 2? It is an eats DC, so where will we bound to? 2/3. Okay, so far so good. Okay, how about number 3? It is a Boten. Okay, so it doesn't have a horizontal asymptote. That means that it is a does not exist, but typically if we are going one-sided, a one-sided limit, which a negative or positive infinity really is a one-sided limit, we want to be more specific. So if I'm going off to a negative infinity, how do I tell whether my y values are going up forever or down forever? Yeah, we plug it in. So if I'm getting bigger and bigger negative numbers, what's going to happen if I plug in -10? Do I get a big negative number or a big positive number?
Big negative.
Big negative. So my -10, I don't need to actually know what that value is. Who cares? But it's going to be a really big negative number over 2. And then if I plug in larger negative numbers, or in the negative direction, plug in -20, -30, they're just going to keep getting bigger negative numbers. So where's our limit headed? Negative infinity. Okay, so very similar in number 4. We get a Boten again. So we're bigger on top. There's not a horizontal asymptote. See if you can decide whether it is going to a positive infinity or a negative infinity. Okay, what do we think? Positive infinity. We agree or disagree with Matthew? Matthew the Bold saying positive infinity. How do we know that? Okay, So wait, are we plugging in negative values or positive values? Okay, so we're, for this one, so be careful because well, and this is typed really small.
Give it a try.
Yeah. Yes, okay, so we're going to a positive infinity, so we're plugging in positive values. Now this guy right here will be negative, but yeah, this one's going to outweigh anything that has a higher power is going to outweigh something with a lower power. So we know that overall the numerator will end up being positive and the denominator will end up being positive. So this is going to keep getting bigger and bigger positive numbers. Eventually, what we wrote in our flip books during Encore, L'Hopital's rule, will help us with something like that if it's less, I don't know, not as easy to see what's going to happen with it over time. Oh, L'Hopital will help us out. Okay, questions there with limits at infinity? Okay. So on the back, we are looking at, we've looked at these rules before. We've got one that is new to us. The rest are not. The first several rules, so you're like 1 through 6. 6 is looking kind of funky, but I think it's just the way that it's typed. Your 1 through 6 are pretty intuitive. So whenever you're finding the limit of two functions that are added together, then you can find the limits separately and add them together, that kind of thing. So let's go ahead and look at the A through C here goes along with that vibe. So they're letting us know that, with your rules up there, if I'm finding the limit as x approaches -2 of this f of x times g of x, that I can find those limits separately on each graph, and then I would be multiplying them together. So what do we think the limit is as x approaches -2 for f of x? Yeah, it looks like -2. How about for g of x? Yeah, -3. So this limit would end up being 6. If either of yours end up being a does not exist, it doesn't matter what operation you're doing. If you're adding, subtracting, multiplying, dividing, and one of them doesn't exist, then the overall limit doesn't exist. For B, we threw in some scalar multiples, but it really doesn't make it too much crazier. You've just got 4 times whatever your limit as x approaches 3 of f of x is. What is the limit as x approaches 3 of f of x? Good job. So we're looking at what it's approaching, not what that value is down there. So it looks like 3. And then same thing for g of x. Yeah, looks like 3. Might be slightly below, but we're not going to mess with it. Yeah, 21. Yeah, and then you can go and work through the last one. Looks like several of you are already. Let's see, we've got. Okay, so on C, can we confirm or deny a 1/2? So, questions on A through C? Okay, so finding them individually, really just plugging it in. Okay, so our new part is this part D and E, and this is a little bit strange, maybe not as intuitive as the other ones. So this is the rule number 7, and it's telling us that if we have, it's giving individual limits, so the limit as x approaches c of g of x is L, and the limit as x approaches c of f of x is f of L. So we're plugging one of them into the other. Really, I feel like this part is the most clear, that if I'm finding the limit of a composite function, so we've got limit as x approaches c of f of g of x. I'm actually only going to find the limit of the inside, so I'll find the limit of g of x, and then I'm going to find f of that. So the only part you actually end up finding a limit of is the inside part, and then you plug it into the other function. So not as intuitive as we would think, especially after looking at the other ones. So looking at D together, so if you've got this limit as x approaches 2 of f of g of x, then our f is going to be on the outside. We're actually just going to find the limit as x approaches 2 of g of x. So what do we think? What is the limit as x approaches 2 of g of x? Sounds good to me. So right there. So we are left with f of 5. And then for this part, we're not finding a limit, we are finding a value. So now we're going to our function and saying, what is f of 5? And it looks like 0. Yep. And that's what we've got. So finding the limit of the inside function, and then we're just plugging it into the outside one. Okay, go ahead and try E. Okay, this tape is the worst. Okay, so what do we think for the limit as x approaches negative 2 of f of x? So we should have negative 2 for the inside, just looking at as it approaches a negative 2 here, it's approaching a negative 2 for the y value. And then we're just looking at g of negative 2, which happens to be the same as the limit, but that's not always the case. So maybe we end up with, at the end, we have a g of 1, and then that would be the difference between us saying, okay, then overall it's 3, versus it does not exist. So that last part is not a limit, we're just evaluating at the function. Okay, so a little different. We'll see those every now and again. Not a major concept, but every once in a while. The last thing is a theorem that is less important than our 3 big theorems, but it does come into play every now and then. This is called the Squeeze Theorem, and it's pretty intuitive. It tells us that if we've got a function that is always in between 2 other functions, so if h of x is always below f of x, which is always below g of x, which could look a lot of different ways, but it just means that, you know, if this polynomial is your f of x, then that means for every single value, g of x, which it says it could equal it, so it could touch it, but it's below it forever. And then your g of x would have to be above it forever, but it could also touch it. So if we've got this where one is below the middle one, which is always above the top one, or below the top one, And then we also know that the limit as x approaches c of the top and the bottom one are the same. So this is saying that your limit as x approaches c of h of x and as it approaches g of x, so our bottom and our top, end up being the same thing. Then that means that the limit as x approaches c of the middle function also has to be that. So wherever they're right here, so they're squeezing them together, that's where that squeeze theorem comes from. So if this is the c value, and we know that this one's always below f of x, which is always below g of x, but the limit as x approaches c of h of x is 5, and the limit as x approaches g of x, or x approaches c of g of x is also 5, then that means that the limit as x approaches c of f of x has to be 5. It squeezed it together. Kind of like the intermediate value theorem. It's like, sounds way more complicated than it is. Do it. On the test? What test? Oh yeah, sure. Now, it's not one of the major ones that we're guaranteed to have on the test. There are certain ones that I know exactly, like some of the types of problems I can tell you exactly what's going to be on the AP test. But then there are some random ones in there. There was a squeeze theorem problem on one of the free response questions. It's been 2 or 3 years. 2 or 3 years ago, and it threw a lot of people for a loop because it wasn't really a major theorem. People were mad about it. It wasn't really a major theorem that people covered a ton in their classes. You just kind of like go over it and move on. So a lot of people did not do well. I think the average score on that was like a 1 or 2 out of 9. So it wasn't great. So we'll make sure that we know our squeeze theorem. I would say it's unlikely that it ends up being a free response question again, but who knows? We'll just know all the things. Okay, so for example, if they tell us that g of x is always trapped in between 2x and this x to the 4th minus x squared plus 2 for all of our x values, and then we're looking for this limit as x approaches 1 of g of x, the nice part about the squeeze theorem is that the wording alerts us that it's talking about the squeeze theorem. So if they say anything about a function always being below 1, which is always above another one, or if they start out with just an inequality like this where they're saying it's trapped in between these two functions, the squeeze theorem is going to be, there's very few times that we're looking at something like that where a function is stuck in between two other functions. So what we're going to do is look at the limits of the other two pieces. So we're going to look at the limit as x approaches 1 of 2x. Which would be loud and proud.
2.
Yeah, it would be 2. Like 2 times 1 is 2. You're right. Same thing for the other function. So this might take a little bit more doing, but not much. Okay, so we get 2 for that one as well. So we don't even have to know what g of x is. It doesn't matter what the function is. But if it's always in between these two pieces for every single value of x, that means that the limit as x approaches 1 of g of x also has to be 2. And we'll look at that AP question from a few years ago. It's going to take a little bit more explaining. I forget what all it involved, but for something like this on an AP question, maybe we would be more of explaining, I know that the limit is 2 because the piece that's always below it, and showing this, the limits are 2. So by the squeeze theorem, the limit as x approaches 1 of g of x also has to be 2. Okay. Questions while we're here? Sometimes it's hard to know what kind of questions you're going to have with just one example, but